Hey, Wade, now let's go ahead and talk about the addition rule. So the addition rule is actually used to calculate the probability that either or both of two events will happen. And it's listed on this sheet. We have the probability of A or B is equal to the probability of A plus the probability of B, and then minus the probability of both. And it says we can actually subtract this probability of both to avoid double counting. So we're going to see how that plays out in our examples. But the addition rule is similar to the multiplication rule, except instead of multiplying, we're actually adding, and then we're adding that last part of it where we subtract the probability of both. So there's a special case of the addition rule that I definitely want to talk about before we get into our examples, and that's the idea of mutually exclusive events. So if two events are mutually exclusive, then they can't both happen at the same time. So if they can't both happen at the same time, when we subtract that last term, the probability of A and B, we actually get a probability that's zero. So it says if they both can't happen, what's the probability of A and B? And it's actually 0. So this simplifies the addition rule if we have mutually exclusive events. So the simplified version would just be the probability of A or B is equal to the probability of A plus the probability of B. I always, just to be safe, rather than, it's always good to check, are the events mutually exclusive at the beginning of any calculation? But just to be safe, I always add that last term so I don't forget it. And then if it's 0, just not include it. But technically, if you have mutually exclusive events, really the probability of A or B is just the probability of both added together. So we can maybe see this a little bit better through some drawings. A lot of times when statisticians or data scientists or maybe computer scientists do this as well, are thinking about probabilities, especially OR probabilities, they use these Venn diagrams for two events. And it tells us to draw the scenario for both mutually exclusive and non-mutually exclusive events below. So mutually exclusive, we'll start with that. The mutually exclusive case means that the two events cannot happen at the same time. So if I was going to draw a Venn diagram, it would look kind of boring. I would have event A over here and event B over here. There's no overlap where they happen at the same time. But if the events are non-mutually exclusive, that means they can happen at the same time. There is this idea of the overlap. So I would have event A and then event B, and then this right here, this intersection, is the probability of both. Or whenever I say the probability of both, I mean the probability of A and B. So a lot of times you'll hear this section right here, this probability of both, referred to as the intersection. And the intersection of two elements of a set is basically all the elements that are common to both sets. And a lot of times I'll use this symbol for intersection, which is an upside down U. But Wade, I think you have a slightly different symbol, right?
Yeah, in Boolean algebra, we often use a small v to represent an OR symbol.
What about the and symbol?
The and symbol, flip it over, and it's kind of a caret.
Perfect. So to represent the intersection, Wade and computer scientists use the little caret. I see the upside down U a lot, but they mean the exact same thing. And then what about for the union?
The union, that's the OR, which I gave you in the beginning.
Oh, you gave me that already, which is that you said that was a V, right?
That's a V. It's basically the caret turned upside down. So sorry for confusing you there.
No worries. It says the union of two sets is the set that contains all elements of both sets. So the symbol for union that I use is U, and then the symbol that Wade uses is V. But they mean the exact same thing. So now that we know all about the addition rule and this idea of union and intersection, we can do our puzzles. So the first one says, what's the probability of getting a 3 or a 4 on one roll of a die? And then are the two events mutually exclusive? So let's think about the mutually exclusive part first. So here's a die for you, Wade.
Yeah.
We want to roll once and look at the two events getting a 3 or a 4.
So I could get a 3. Or I can get a 4, but there's no possible way for the die to be both a 3 and a 4 at the same time.
If I'm only rolling once, right? So this would be an example. So mutually exclusive, if we look back at that definition, we said that mutually exclusive means that the two events can't both happen. So these would be mutually exclusive events. So I'm going to say, are the two events mutually exclusive? Yes, because you can't get exactly what Wade said. You can't get a 3 and a 4 on one roll. So if I was going to calculate this probability, I would say the probability of getting a 3 or a 4 is equal to the probability of getting a 3 plus the probability of getting a 4, and then minus the probability of both. But we just said we can't get both, right?
Yep.
So I'm just going to say this is 0. So what's the probability of getting a 3?
So 1 out of 6.
Plus the probability of getting a 4.
Also 1 out of 6.
And we get 2/6 or 1/3. So I'm just going to leave my probability like that.
Awesome.
So the second puzzle asks, what's the probability of drawing a card from a full deck and getting either a heart or a queen? And then are these two events mutually exclusive? So Wade, do you think these are mutually exclusive, heart or a queen?
So mutually exclusive is, can they happen at the same time? So a queen of hearts.
Oh, my favorite card. Yes, we can get the queen of hearts. So if they were mutually exclusive, the two events cannot happen at the same time. We have to ask ourselves, can they or can they not? And they can. So I'm going to say no. Are they mutually exclusive? No, because you can get the queen of hearts. So I need to keep that in mind. I want to definitely make sure to subtract that probability of both of the queen of hearts to avoid double counting it. I don't want to count it as a queen and count it as a heart and have the wrong probability. So we want to know what's the probability of getting a queen or a heart. And that's going to be the probability of getting a queen plus the probability of getting a heart minus the probability of both. So how many queens are in the deck? What's the probability of getting a queen?
So in the full deck, it's going to be 4 out of 52.
4 out of 52 plus probability of getting a heart.
So there's 13 hearts, 13 out of 52.
And then minus the probability of both.
Well, there's just one heart that's also a queen. The queen of hearts, your favorite card.
My favorite card. And we definitely have to make sure, I know it's only 1 out of 52, but the question would technically be wrong if we didn't do that. So simplifying this, I get 4 plus 13 is 17 minus 1. I get 16 out of 52. And that is my final answer. So very, very last question for the addition rule. It says, what's the probability of drawing a card from a full deck and getting either a heart or a spade? All right. Are the two events mutually exclusive? So we have to ask ourselves, can we get a card that is both a heart and a spade?
So I don't know of any cards that's multi-suit. So
Spade of heart, no. Yeah, so I'm going to say yes, because you cannot get a card that's both a heart and a spade. So if I want to calculate this probability, the probability of getting a heart or a spade, I'm going to use the addition rule again. This is equal to the probability of getting a heart plus the probability of getting a spade. And then I don't like to be risky, so I'm always just going to write this out as the probability of both, but we know that this is technically 0.
And I do the same thing. I always write out that minus, just because if you don't, you begin to forget it.
You begin to forget it, and I see students do that all the time. So it's always good. When in doubt, write it out. So the probability of getting a heart, we said there were 13 hearts in the deck, so 13 out of 52. Plus, how many spades are there?
Also 13 spades.
Also 13. So this is 26 out of 52, also known as 1/2 or 50%. And again, we've seen the addition rule in action here. So that's all we have for this video.
A lot of great examples.
Keep nerding out.